Thanks for the invite to be here. I'm going to be giving you just some general background on the Earth as the climate system of the Earth, concentrating on the relationship between the sun and the atmosphere, the ocean, and the radiative balance, which is the sort of the essence of the climate system. So I'll give you an introduction. I'll talk about blackbody radiation, the sun and the Earth as black bodies, the radiative balance of the Earth, and then I'm going to go into the greenhouse effect, which I say I'm going to make it simple, but it's about 30 slides, so you can get an idea of how simple it is. And I want to concentrate on that because it's really the hardest thing to understand, to visualize, and to figure out what it is. It's so confusing. And, you can read books or go on the web, and most of the people who write about it are confused about it too. And then I'll finish up with sort of a look at the Earth system inside, what's inside. And then at the end, if there's time, I'll talk a little bit about global warming and how the sun's variation in global warming. Next slide there. So, introductory. The Earth is actually a balance between the heat that comes in and the heat that goes back out. So the heat comes in from space, essentially from the sun. The sun, a little bit of the sun is reflected, and then the heat that's absorbed in the Earth system, either in the air or the land, is later re-emitted in the infrared as blackbody radiation. I'll explain that later. And so there's a very close balance between how much solar heat comes in and the amount that's radiated back out to space. And if there wasn't that balance, the Earth's temperature would be constantly changing by a lot. So you've heard about the greenhouse effect. The greenhouse effect has to do with the profile of temperature in the atmosphere. And it's really a measure, you can think of it as the difference between the surface temperature of the Earth, how warm it is where we're walking around down here, and what the radiative temperature of the Earth is. In other words, that energy we're radiating back out. And that difference between that profile of temperature in the atmosphere is strongly affected by these greenhouse gases. Water vapor, CO2, things like that. Now, the climate system, the internal part of the climate system, the atmosphere, the ocean, the land, the winds, the currents, the clouds, they redistribute heat within the system. And that also affects this net greenhouse effect. So. Now, that means we need to switch to the other section. If you can find it. Not that one. It's already up. I'm not sure that's the right one. So I already had it up in somewhere. It was probably that one. I know they had the same title. I made a few changes. Okay. So, I want to talk now about this blackbody radiation and the planetary energy balance. And that's how we'll get into the greenhouse effect. So, the topics I'll discuss here are just the electromagnetic spectrum, radiation, the relationship, the blackbody radiation and how it's related to temperature, the sun's heat at the Earth, and then how the radiation goes back out to space to balance the sun's heat. This idea of the radiated temperature of the Earth, and finally the surface temperature of the Earth. So it's the difference between these two, which is the simplest way to characterize the greenhouse effect. So this is the spectrum of radiation as a function of, in this case, it's wavelength of the radiation. So microwaves, like your microwave oven that has a wavelength about this big. And visible light, the light you see with your eyes, has a wavelength in the 0.1 to 1 micron range. So that's microscopically tiny. The sun also produces ultraviolet. And then X-rays, when you get your arm X-rayed at the doctor, those are really, really short wavelengths and high energy. So next slide. Now the idea of blackbody radiation is any object or body that has a temperature radiates radiation, and the wavelength of the wave, it's spread across wavelengths like this. So it radiates a spectrum of frequencies or wavelengths. And if a body is absolutely black, it's a black body. And that means it radiates the maximum amount of radiation at that temperature. So you can have bodies that are not black. Usually we say they're gray. So a gray body would radiate less radiation than a black body. And you'll see this reduction in the amount of radiation characterized with this thing called the emissivity. It just means how effectively does it emit radiation. So that emissivity is a characteristic of how gray or how non-black the body is. So emissivity is 1, it's absolutely black. And it radiates the maximum allowed by nature. If emissivity is 0, it's a perfect mirror. Nothing goes in, nothing comes out. And this, you'll notice that this wavelength dependence of the radiation coming out has a peak in it, and that peak is sort of given by the 1 over the temperature. So the hotter it is, the shorter the wavelength that it is. And if you sum up all the radiation over all wavelengths and say what's the total energy emitted by the object, then it goes as the temperature to the 4th power. So if you warm something up just a little bit, you get much more energy out of it. So next slide. So that's this basic concept of infrared radiation. So all objects emit radiated energy. The hotter they are, the more they emit. The amount of energy is proportional to the 4th power of the temperature. And you can actually write this simple equation which describes it. The flux of energy from the body is this coefficient sigma times T to the 4th, and that's absolute temperature. And this coefficient has a known value. Not only is it a known value, it's an easy one to remember because it goes 5, 6, 7, 8. So that's the only one I've ever been able to remember. So the funny thing about this now is this characterizes something you're not used to thinking about, and that is the energy flux. So what is a flux? So when you came this morning, there was nobody in this room, and then 31 people walked into the room. That was a flux of people into the room. So when the flux was over, there was more people in the room than when it started. And that's why we worry about fluxes. We're kind of trying to keep track of where things are going. And a flux is a funny kind of a thing. It's the number of amount of stuff per unit area per unit time. So to get the flux of people into this room for a scientist, you would have to take the number of people that went through the door, divide that by the area of the door opening, and then divide by the amount of time it took all of you to get in here. And then it would be 7 people per meter squared per minute was the flux of people into the room. And in this case, it's not people per meter squared per minute, it's watts per meter squared. Remember, watt is the amount of energy per time. So you can think of it as so many calories per unit second per energy. So when you eat food, you have a flux of energy going in your stomach, how many calories you take in, divided by the area of your mouth, times how long it takes you to eat dinner. That's an energy flux. All right, let's go to the next one. So, the interesting thing about the energy flux from these two bodies is they're wildly different temperatures. So the Earth is at about 300 Kelvin, the Sun is at about 6,000. So the amount of energy coming from this is much bigger than the amount of energy flux from the Earth. Because remember, it goes as temperature to the fourth, and the Sun is much bigger than the Earth. So next slide, please. So now, on this graph, I repeated this spectrum graph again, only now I've shown the Sun and the Earth here. And you notice the Sun's emissions are mostly in the visible, but the Sun emits lights you can't see with your eye. And the emissions from the Earth are at a much lower frequency or longer wavelength. And you can't see those at all. Can't see infrared. There's actually a tiny bit of overlap between the two. And this difference in the wavelength of where these things fall is another important part about the system, because the properties of what happens to the light when it encounters the atmosphere, the ground, the clouds, is highly dependent on the wavelength. There's a big difference between short wavelengths like solar light and infrared wavelengths. So the next slide, please. All right, so I just kind of summarized this here. The Sun is 6,000 K. The wavelength is about half a micron, very small. It's visible. The Sun is green. I know it doesn't look green, but its peak in the frequency is green. And the amount of flux coming from the Sun is 7 times 10 to the 7th watts per meter squared. The Earth around 300 Kelvin. The peak of the wavelength is about 10 microns. It's in the infrared, and the flux is on the order of 460 watts per meter. Okay, next slide. So that's the Earth. And let's now talk about this energy balance here. Next slide, please. Okay, so one tricky part about this talking about the energy balance is that we've been talking about the flux, which is watts per meter squared. So when the Earth emits, the area of a sphere is 4 pi r squared. So the total energy emitted by the Earth is the flux times the area, which would be 4 pi r squared. But when the Sun shines on the Earth, the Sun does not shine on the whole area of the Earth at the same time, because half the Earth is in shadow, and also the Sun's rays don't come straight in all over, they come at angles. And so the effective area of illumination of the Sun is only pi r squared, and you can understand that easily if you just imagine you shine a light at a sphere, and then say how much energy is this sphere taken out of the light beam. You can see the shadow on the wall of a sphere is just a disk. So the area of light removed is pi r squared, the shadow of the Sun. So next slide. So the energy delivered by the Sun just falls on part of it, but the radiation, the IR radiation, comes from everywhere. Next slide. Now the energy balance is simple. The Sun energy in averaged over the sphere has to equal the energy out that's radiated. So next slide. And if you use that, this is saying what is how much energy does the Sun emit and at the Earth. So that's this thing called the solar constant. So we take sigma t to the 4th of the Sun. Remember that's 6,000 degrees. And then it comes out of the Sun at the radius of the Sun as a sphere. It spreads out over a sphere, which is the radius of the Sun-Earth orbit. So that reduces the intensity of the Sun's watts per meter squared by this large factor. And so that is the radius of the Sun-Earth orbit is about 10 to the 11th meters, and the Sun is about 10 to the 9th meters, so you get this number here, 1368, approximately, watts per meter squared. That's how bright the Sun is at the Earth. Of course, the Sun is a lot brighter at Venus, and it's a lot dimmer at Mars. If you want to know how bright it is at Venus, you put in the radius of the Sun-Venus orbit. And if you want to know it at Mars, put in the radius of the Sun-Mars orbit. Okay, next slide. So, now we want to quantify this balance. So the energy N is the Earth's constant times the pi times the radius of the Earth. However, sorry I misspelled that, but some of the energy is reflected. So next slide, please. So we take that into account by using something called the albedo. I have no idea why it's called the albedo. It just means if you send a watt to hit the Earth, it doesn't absorb the watt. Part of it is reflected. So the Earth isn't completely black in the solar spectrum. So some is reflected back to space, and so 1 minus the reflection is the amount of energy absorbed. The Earth's albedo is about 0.32, 0.33, 0.34, depends on who you ask. So that reduces the total energy absorbed in the Earth system. So how much does the Earth lose? Well, it's 300 Kelvin, so it has, it's just, the flux is sigma t to the 4th, the area is 4 pi, so that's how much the Earth emits in the program. So you can balance all that up, and you can get a simple equation balancing, and that factor of 4 comes from the area of the sphere versus the area of the disk. Next. So that allows you to calculate this temperature. The solar constant, 1 minus the reflection, 4 times that, 5.67 minus 8. That is the black body temperature of the Earth, or effective temperature that the Earth radiates to space. So I brought my little gadget here, somewhere on the table. Yeah. This is an infrared thermometer you can buy to measure your kid's temperature by, you stick it in their ear and you press the button, and it measures by infrared. So how does it work? Well, it measures the flux and then divides the flux by sigma and takes the 1/4 power in a microprocessor in here, and that's the radiative temperature. So if you took this thing, got in on the space shuttle, went out into space and pointed it at the Earth, you can measure the Earth's radiative temperature. So next slide. So what is that? Well, you put in the solar constant, the albedo, 5.67 minus 8. And that's T to the 4, so you take the 4th power. And so the Earth's radiative temperature is 252 kelvins, which sounds kind of hot. Next slide.
Can I ask a question?
Yeah.
It says T space. Not
Yeah,
T
I'm just T radiated to space.
space. So you take the 300 degrees radiative temperature of the Earth minus that?
Now the 300 is, yeah, that's the surface temperature.
That's the
This is the radiative temperature. You're getting ahead of me.
Oh, I'm sorry.
Okay, so that's Kelvin. So remember, you got to subtract 273 to get centigrade. That's -4 Fahrenheit. So that's cold. So it ain't that cold, right? Am I right? Okay, next slide. So no, the surface temperature is different than the radiative temperature. The difference, the temperature between the ground temperature and the radiator temperature, it's about, I see I've been playing around with the numbers, but it's about 36 degrees. ground is 36 degrees warmer than the radiative temperature. If you stand out in space and point this at the Earth, you get minus 18 or minus 20. If you just take this in and point it at the ground, you get 15. The difference, 36 degrees. That is due to the greenhouse effect. Okay, next slide. So that leads to the million-dollar question, what the heck is the greenhouse effect and what causes it? And the simplest characterization is it's a warming of the Earth's surface caused by the absorption and re-emission of infrared radiation by the atmosphere. Remember I said all objects radiate? Air molecules are objects. So every molecule radiates and reabsorbs infrared radiation. The molecules in the air also absorb and scatter solar radiation. So that tells you, but it doesn't explain very much. So next slide. Now we're going back to this business about the sun and the atmosphere and the Earth. So the sun shines on the whole planet. A certain amount is reflected by the clouds and the air. A certain amount is reflected by the ground, the water, trees, land. Then a certain amount is emitted by the Earth and the infrared, sigma T ground to the fourth. Some of that that's emitted is reabsorbed in the atmosphere and re-emitted, and the atmosphere emits. So it's kind of a complicated mess. And this is the simplified version. So, next slide, please. Now here's some little factoids about the whole business. The solar flux is moderately scattered and weakly absorbed in the air. So air doesn't absorb solar radiation very effectively. It kind of scatters, but not that great. So when you go out on a sunny day, it's hot. IR flux is strongly absorbed and emitted by greenhouse gases in the atmosphere. Very strong interaction. Water vapor, CO2, ozone, methane are the principal gases. So the atmosphere is 98% oxygen and nitrogen, and they are not greenhouse gases. They don't interact strongly with infrared, weakly but not strong. Solar photons, solar light, when they're absorbed in the system, they never get re-emitted, essentially never, as solar. You don't have little suns, glistening all over the planet. When they're absorbed, if they get re-emitted as radiation, they come back in the infrared at the temperature of the object. If the Earth heated up to 6,000 degrees, then the Earth would look like the sun. So a key issue is the process in the atmosphere of adjacent layers of air that kind of absorb and re-emit radiation. They talk back with each other. So there's another issue is all the mixing in the particle by clouds and turbulence and storms, which complicates things. The greenhouse effect warms the surface, does not affect the mean radiating temperature of the planet. The greenhouse effect cools the stratosphere. This is a tricky issue, but the mean radiating temperature of the planet is not affected by the greenhouse effect. If the surface gets warmer, somewhere else has to get cooler to balance it out. Right? Turns out high in the atmosphere gets cooler, low in the atmosphere gets warmer. Kind of ironic. That's what happens. So if greenhouse warming warms the Earth, it would cool the stratosphere. Next slide. Well, now I have some fancy diagrams with equations on it, because in my salary, I have to use equations. So if I use enough in this talk, I can go try and get a pay raise. So now I'm just going to try and give you a more quantitative look of the way the atmosphere interacts. And don't say the equations. There won't be a test. I realize if you have to teach third graders, you won't be going to this kind of stuff. But if you can, bear with me here. So I just want to talk about radiative transfer issues in generic terms for a second. But remember, we have our solar flux down, and we said some amount was reflected, A times that flux, that's that albedo, and some amount passes through, is transmitted by the atmosphere, and the atmosphere absorbs a certain amount of solar radiation, and we use this little, let's call it F, some call it. So the amount getting through the atmosphere is 1 minus F, 1 minus A times solar. So I just earned, another $10. So in the infrared, very similar picture. There's an IR flux down. The atmosphere absorbs some amount, which is our emissivity times that flux, and we transmit 1 minus IR up. There's no reflected. So the atmosphere in the infrared is so absorbing, it just doesn't reflect anything. Maybe a little certain particular things might do a little, but for our purposes here, nothing. So, next slide.
Quick question.
Yeah.
She has a question.
Yeah.
So does our atmosphere heat up because of the energy that it absorbs, or what happens to the absorbed energy?
It does, that is a factor. Some of the energy absorbed in the atmosphere heats it up. It's just that the solar heating of the atmosphere in the lower atmosphere where we live is small compared to the other modes of heating the atmosphere. When you get up in the stratosphere, that's all the heating that the air gets, just from the sun.
So
So it's complicated.
do we just like not absorb a significant amount of the sun?
We don't absorb a lot, because, air is pretty damn clear to some of us, right? That's kind of the thing. It's a factor, but it's not, in the Earth's atmosphere, it's not a dominating factor.
I have a question.
Yeah.
When you talk solar flux versus IR flux,
Yes.
is solar flux the whole electromagnetic spectrum or visible?
It's just the part coming from the sun.
Right.
So you remember that diagram I
Yeah.
showed where it was the yellow part? So it's from about 1/10 of a micron to about 1 micron. Just that. And you can see most of it, but there's parts you can't see, like ultraviolet, and there's some near IR you can't see. That's the part that comes from the sun is limited in wavelength range. Now this is the Earth system, it's just the same diagram, but I've now made it a little more, I put in the factor 4, and then I have the atmosphere. Now what I left out of the other diagram, which is the key to this, is the atmosphere. Yes, it has infrared radiation coming off the Earth, being absorbed and passing through, but there's essentially no infrared radiation coming from space. Space is cold. There's not much matter out there, and what matter is out there nearby is cold. So there's no IR flux coming down. But remember, every object that has a temperature emits. So the atmosphere is emitting infrared radiation according to epsilon sigma T to the 4th, where T is the temperature of the atmosphere. So this diagram is fairly complete. It's the simplest diagram you can draw that contains the essence of the Earth's climate system at the atmosphere. It has the Earth emitting radiation at the ground temperature, absorbing some of that and letting some go through. It has the atmosphere emitting radiation at the atmospheric temperature, and it has the sun passing through. Some is absorbed, some is absorbed on the ground. You can take all these fancy equations and put them together, and hit the next slide there. You can now compute the greenhouse effect based on those simple equations. And there's an equation for the ground temperature in terms of the variables. And notice this part here is the mean radiated temperature. So the ground temperature is related to the mean radiated temperature. There's these two factors, one having to do with the absorption of air, the solar flux, and one having to do with the emissivity of the Earth's atmosphere. That little circle up there is the Earth. That's where the Earth lies on this diagram. The Earth's atmosphere absorbs about 8% of the solar flux going through it. And the Earth's, that's this variable here, and the Earth's emissivity is about 0.89. The numbers mean nothing, of course. They're just numbers. You wouldn't be able to guess ahead of time what they were. Now, suppose, and you'll notice I put in the Earth's parameters, 0.08 and 0.89 for emissivity, so that number's 0.08, that number's 0.89. And I get this radiating temperature up there. That's the 15 degrees of the ground temperature. But suppose the Earth atmosphere was a lot more absorbing than it is. Suppose it said instead of absorbing 8% of the sun's radiation, it absorbed 50%. What would the greenhouse effect be? Well, you just look here where the absorption coefficient is 0.5, that means it absorbs half the solar, and you look up and the greenhouse effect would be 10 degrees less. So the surface of the planet would actually be 10 degrees cooler if the Earth's atmosphere was more absorbing. So, just for fun, I tried to do this with Venus, and you can't, it doesn't work. Venus is an extreme greenhouse planet that's closer to the sun, so the S0 is bigger, but its atmosphere has got a lot of air in it, mostly CO2, and it's got a lot of CO2, and it's very dense, so you can't do a simple one-layer model like this to characterize Venus's atmosphere. The surface temperature at Venus is 600 degrees Kelvin, which is enough. Lead is molten at the surface of Venus. Yeah. And if Venus didn't have an atmosphere, the surface temperature of Venus would be about 420 degrees Kelvin. So a big difference by the greenhouse. So would you go back one slide, please? If on this diagram, there's one thing that says what the greenhouse effect really is. So remember, we have the sun shining down, going through, and a certain amount is absorbed, and comes down, and you go outside, you feel that solar heat. This is the infrared flux emitted by the atmosphere. That is coming down too. That's additional heat coming from the atmosphere that is warming the surface. And that is a big number. So it's like 400 watts or so. And that, if you want to say one thing, what's the greenhouse effect? It's this extra infrared heat coming from the atmosphere. Okay, go ahead. So I just want to say one thing about greenhouse analogies. The greenhouse effect is called the greenhouse effect because it's an analogy with a greenhouse. So, and of course, scientists like to say, well, you know, a greenhouse effect is not really like a greenhouse because in our pay grade, we have to make it more complicated than that. And the fact is, I'm not an expert on greenhouses, but as I understand a greenhouse, it's a big house made of glass. The sun shines through, the air is trapped in there. Infrared re-emission doesn't enter into it very much. It's mostly because the air doesn't blow through it. I think if you took the walls off the greenhouse and the air blew through there, it wouldn't be a heck of a lot warmer in there than anywhere else. That's why it's not a great analogy. So I heard another analogy about the greenhouse effect characterizes driving the length of Broadway through Boulder, trying to navigate all the construction, the lights, traffic, and students sprinting in front of you across, go through the university. If they added a couple of lights, you know, like if there was more CO2 in the atmosphere, analogy. If they added a couple of lights, it would take you longer to get through. So the idea is that these air molecules are jamming up things and the IR is getting stuck down on the ground. So maybe that's a good analogy, I don't know. So I like the analogy of what I call cut of dirt, which is a great routine from Brian Regan, if you've ever heard it, because he wakes up in the morning and he realizes he hasn't done his science project that's due that day. So on the way to school, he gets a cup of dirt and he goes in, and that's assignment. And you guys have right here a cup of dirt. I was amazed. So this is an analogy. I don't know if this would work, but if you put a layer of a sheet of glass or plastic that was opaque in IR but transparent in solar, and just laid it over that, shone your light on it, with your thermometer you would see what the temperature of the dirt was. That'd be the ground temperature. Take your IR thermometer and point it at the top. It would see the glass, and that would be cooler than the dirt. That is a pretty good analogy to what's happening in the glass is kind of taking the place of the atmosphere's emissivity. Okay, I think we're on to the, let's see what's next. Okay, back to the other talk.
Chris, there should be water over there.
Yeah, it should be open. I don't know if this is the right one or not. Okay, so this is a review of what we looked at. We have again, I don't want to beat it to death, but the sun's coming down. Some of it is reflected back. Some is reflected from clouds, some is reflected from dust, air molecules, and some by the surface. A little bit of that sun is absorbed in the air. Most of it is absorbed at the surface. Then the surface emits IR, some of which passes through the atmosphere and goes to space. But most of that's reabsorbed in the atmosphere. And then the atmosphere is remitted back down, and the atmosphere is emitted to space. And then within the Earth system, there are other complicated physical processes that are moving this all over the place. Just for your information, if you look at the sun, actually is not the only thing that puts heat into the Earth system. It's about 230 watts. There's another one having to do with dissipation of the motion of the air gets converted to heat, so that's about 2 watts. Photosynthesis, all the plants, they actually are the other direction. They turn solar heat into wood, so they remove heat. There's geothermal heat flux from the ground caused by the radioactive decay in the Earth. And then there's the heat we generate by burning fossil fuels. Pretty small number right now. Yeah.
Actually, I have a question from the previous slide.
Yeah.
When we take a look at it.
Yeah.
So the surface radiation that is absorbed once again by the atmosphere, why
Yeah.
is there such uneven distribution both up and down? So I see back radiation, we're
Yeah.
looking at almost twice.
Good question. 2 reasons. The Earth is radiating as almost a pure black body. So its epsilon, its emissivity, very close to 1. The Earth temperature is 15 degrees centigrade. So the atmosphere, it's air, right? So its emissivity is not 1. It's actually lower. Plus, the atmosphere is colder. So, by the time you're in the stratosphere, the atmosphere is minus 50 centigrade. So those 2 factors combine to make this smaller than what's going up.
Right, I guess I see that, but, so, the back radiation, so even going into space, up into 165, why is it so much smaller? I mean, why isn't our atmosphere evenly distributing energy both up
Yeah.
into the space and down?
I was afraid you would ask that question. Because you remember in the little model I showed, they were the same. Right, so that has to do with the multi-layer. You can't really treat the atmosphere as one chunk. It gets more complicated than that. And also that thing I mentioned about the way the turbulence and everything mixes it. So the profile of temperature in the atmosphere is affected by more than just the radiative element. So those things kind of combine to make this not as simple. Another big factor I completely did not discuss is the effect of clouds. So clouds are tend to be very black. So they radiate as black. Their emissivity is very close to 1. If they're in the lower atmosphere, because they're water clouds and they've got a lot of water in them. Whereas if you go into the upper atmosphere, like cirrus clouds, the ones that are thin, way up there, their emissivity is lower. So the clouds are another reason why this is bigger going down and up. So you guys are sharp, because that number is not consistent with that little one-layer model I showed. I was hoping you wouldn't catch me, but you did. Okay, next.
Can I ask a question?
Yeah.
Does that, the surface radiation, the back number, does that change between land mass and water?
This one here,
Yeah. So does the number?
the stuff coming down from the atmosphere.
Yes.
Yeah,
but
it
goes
does
down.
a
You're
little
talking about
bit.
oxygen,
Mhm.
you know, what happens in the oxygen?
Well, it does change a little bit, and it would depend on where you are. Now, it turns out that this coming down is strongly dependent on the temperature of the air above you. So if you're at the South Pole in Antarctica, it's a small number, because A, it's cold, and B, it's high pressure, and C, it's low pressure, C, it's very dry. So the water vapor is a dominant factor in this, besides that affects this emissivity. So if you're down south where I grew up in Tallahassee, Florida, there's a lot of water vapor in the air, and you get a lot of heat from the air. For example, that's why it stays hot all night long. Whereas in Colorado, there's not much water vapor in the air. At night, in the summer, yeah, it's 100 during the day, but during the night, it cools off a lot. That's because there's less water vapor, and this number coming down is lower. Any more questions? Okay. Okay, keep going. Okay, now we were talking about the seasonal effects of the sun. This is just the geometric effects now of the fact that the Earth's orbit, too bad you deflated all the Earth's there. The Earth's orbit is tilted, and then as the Earth goes around the sun, the direction the tilt is pointed changes over a 1-year period. Of course, at any given time, the Earth is spinning on its axis, and the sun goes up and comes down because the Earth is spinning. So I just graphed here the amount of heat you receive at the surface on a clear day, so no clouds, as a function of the time of year. So this is this downward solar flux at the surface, averaged over the whole day, at 3 places, the North Pole, Boulder, and the equator. And the first thing you notice is that at the North Pole, you have these long periods when there's no sun at all, because the North Pole is pointing away from the sun, so the sun never shines on the North Pole in the winter. Yes?
We just did a whole activity on
Okay.
the season, so
So you guys already know this.
tied into this very well
No, it
today.
ties in.
Yeah,
Great.
excellent. The amusing thing about this, which I didn't realize until I did these graphs, is how the difference between winter and summer in Boulder is pretty amazing. And not only that, I like this. I mean, this is, wow your friends. The North Pole gets more sun in the summer than equator. Kinky, but there you go. Okay, next graph. Now this just shows the, whoops, rather poorly, but it's just showing, this is the amount of sun at the ground taking clouds into account. This is from satellite data, I think. And it's showing the annual cycle, so it's going November, December, January, February. And you can see in the summer, the sun is heating the northern hemisphere. And you see these differences here. There are areas like over South America, you'll notice there's less sun in over here, and that's because of the heavy clouds and all the rainforests on there. So, next slide. Now, I've been talking about, I mentioned about how the atmosphere and the ocean redistribute the heat. This shows, which I won't try to explain because this is not my area and I don't really understand it either. But this shows atmospheric circulations on the from a global point of view. And now you'd think that air would go from like hot to cold. So the equator's hot because the sun shines more, and then the poles are cold. We know the poles are cold. So you would think the air would circulate and exchange the heat between them. And what happens is, because the Earth rotates, everything has to be done indirectly. So it's like trying to deal with teenagers. It just can't go straight. It has to curve, and then it sets up all kinds of circulations. And these circulations kind of define climate zones of the Earth. So you have tropical trade wind areas. You have regions where the winds are westerlies, like storm tracks, things like that. So these, on average, though, these motions do transport heat towards the poles. Sorry, I'm not used to talking this much. Next slide. Keep going. So why is, I mentioned somewhere along here that the ocean is a big factor in Earth's climate. And the reason is the ocean has 10,000 times the mass of the atmosphere. So when you're doing your cup of dirt here, if you had a cup of air, that was the atmosphere, and a cup of water, you can see it takes a lot more heat to warm up that cup of water. And the factor is about 10,000. So if I do the next slide, and another factor about the ocean is, if you just put the sun's energy is absorbed in the upper 20 or 30 meters of the ocean. So that heat tends to stay trapped near the top. So when the sun does not warm the whole ocean, so the surface temperature of the ocean heats up much faster than you would think that factor of 10,000 is telling you.
Dr. Fairall?
Yes.
You had mentioned earlier about the soil example there.
Yeah.
Is it the same depth, 20 or 30 meters, or not?
Well, I was talking about the atmosphere. The soil, it's less than 20 or 30 meters.
Because you hear a lot now about
Yeah.
geothermal.
That's a different issue.
Yeah.
That's heat coming from radioactive decay in the Earth.
Right, but I'm thinking of geothermal heating of a home.
Yeah.
Where you're just using the temperature
Right.
difference between the
Right.
soil and the ground.
And if you get down just 10 feet or so and measure the annual cycle of temperature, you'll see almost nothing. So in the ocean, it's more like 20 or 30 meters. Because the ocean mixes and the soil doesn't.
Yeah, okay.
Now, this is not heat getting into the ocean. This is carbon dioxide, but the principle is basically the same. These graphs are, believe it or not, your taxpayers have paid people to go out on ships and drop things down and pull them back up with water and measure the temperature and also how much CO2 is in it and things like that. And these show a couple of these transects. And what they are showing here is going from 50 degrees north to 60 degrees south, going like this. We're showing the CO2 that humans have produced by burning fossil fuels. Where is it? And you can see it's mostly confined to the upper few hundred meters, and this has been going on for 150 years. So in 150 years, it's only penetrated about that far. So the oceans as a reservoir of heat are very hard to utilize the whole reservoir. So the surface tends to warm up a lot faster than you think. Next slide. And the way you get to the deeper ocean is this, and you may or may not have heard of it. This slide calls it the Great Ocean Conveyor Belt. It describes deep ocean currents that circulate all over the globe. This is the whole planet now. And the only place where water seriously goes down in the ocean is this place off Antarctica and those two places up there off Greenland and Nova Scotia. And so the water sinks in these areas, circulates around, and eventually it comes back up in the surface, gets into the Gulf Stream. So that's very slow, large-scale circulation, which is part of the process that's trying to get heat deep into the ocean, tap the ocean. This is like a 1,000-year process. So when you hear people say, when you pick up the paper, it says, well, the effects of global warming, even if we quit making CO2 tomorrow, the air would keep, the planet would keep warming up or changing and things like that. They're usually talking about these different time scales and adjustments of the system associated with the upper ocean and this deep ocean. So it's conceivable the temperature of the planet might not stabilize for 1,000 years just because of working this kind of thing, which is, this diagram is very fanciful. There's almost no, it's impossible to just measure this one time. So it's been inferred. This is like a great master detective piece to even draw this diagram. So next slide. So I'm going to spend just a few minutes talking about one of my hobbies, which is global warming. So I'm not an expert on global warming. I don't do model forecasts or that kind of thing. More of a hobby. But I think it's a very interesting topic, and there are physical, scientific questions you can ask, and there are political questions and things in between. And one of my hobbies is looking at global warming, information about global warming that's available to the public. Like you can pick up the newspaper, you can pick up Time Magazine, Newsweek, The Economist, you can watch television, Channel 9, you can go to websites, blogs, whatever you want. So I'm not an expert on global warming, but I do know a few things about the physics of the climate system, and I can tell you, you cannot trust any of that. Okay, if it's in the newspaper, you can't trust it. I'm not saying it's wrong, just saying they don't care if it's right or wrong. So, I just did a Google search on something called, I just said, climate warming hoax. Oh, this is the, sorry, this is the old talk. Can I get the other talk up here? Somehow we got the old. It took me a while to find it. It's not in there, it's up there. There you go. Let's go down to there. I could do more. Back one. Yeah. Okay. So I did global warming hoax. 1,530,000 hits for the words global warming hoax. So I'm not an expert on the whole issue, but I know it's not a hoax because I know a lot of serious scientists have evidence that there could be global warming. So they're not liars, they could be wrong. Do you see the difference? I'm wrong all the time. Just ask my wife sitting over there. If you add the word solar to it, you get 240,000 hits. And like just last year in 2007, there was a TV show called The Great Global Warming Swindle. So they're saying all these scientists who work on the IPCC report are liars, that kind of thing. And one of the graphs they show is this one, which shows time since 1860 to today. And on one axis they have temperature anomaly, which is how much the planet is warming. That's this blue thing. They show the CO2 concentration, and then they have this thing called the sunspot cycle length. So, as you know, the sunspots on the sun have like a 22-year cycle, but it's not exactly 22 years, and the length of the cycle varies through time. And so they're using the length of that cycle. This is another graph from an article in the Canadian Petroleum Geology, Volume 50. It's essentially the same graph. It's been reproduced and they've got this. Some things about it that intrigued me when I saw it. They use sunspot cycle length, not the heat coming from the front sun. I just spent an hour explaining why it's the heat flux coming from the sun that defines the radiative temperature of the planet. The graphs stop in 1980. They don't mention the stratosphere. Remember I said greenhouse effect cools stratosphere. If you increase the solar constant, because you put more heat out from the sun, what do you think the stratosphere is going to do? Going to get warmer, right? So, just for fun, I looked into this more carefully. So on the next slide. This is information on the intensity of the sun. And there's two graphs. This is from the last IPCC report. Now, this shows the intensity of the sun since 1600. And the one thing to remember, the sun's intensity has only been measured since 1980. And then they have correlated, they took the data since 1980, correlated it with sunspots and a few other things, and they have reproduced what the intensity of the sun back to 1700. And these guys show two different ways of reconstructing that, and they're different. So this is an honest scientific approach. They're showing you here's two different products, and you judge for yourself how well we know this. And these variations, see the way it's going up and down every 22 years? That's the sunspot cycle. Now, this is another paper from a scientific journal. They've got that very same sunspot cycle length on it. Only on this side of the graph, they show solar irradiance watch from here. So they're saying there's an exact one-to-one correspondence between the sunspot cycle length and the intensity of the sun. And if you notice the difference between 1900 and today, on this graph is about 4 watts, and on this graph it's about 1.5. So remember I gave you that handy-dandy formula for calculating the greenhouse effect. So what they're changing is this number. So if you change that number, you can see how much it changes the Earth's temperature. Use these guys, it's 0.08 degrees since 1900. If you use this one, it's 0.24 degrees since 1900. So if you go to the next slide. Remember the temperature changed since 1900. It changed 0.7 of a degree. So even if you accept this very generous solar variation, you only get about half of the change. So also, remember I mentioned that the graph stopped at 1980, which was kind of a weird thing for a TV show done in 2007. So if you'll hit the next slide, please. This shows what happens if you run the graph to 2007. There's the original graph. They cut it off there. That's what it's done since then. That's the temperature of the Earth. That's the sun's radiation. So I don't think it looks as convincing if you show all the data. And I'm kind of suspecting that's why they didn't show all the data. Another thing about this is they described in a paper that generally described exactly how they produced it. And I went back and took the solar sunspot data and did exactly what they said, and you'll notice it doesn't look as good. So I found that a bit strange. Actually, if they knew what they were doing, this looks better than that because there's a delay between intensity and the warming, just like you guys got the delay when you heated the ground. But they decided the delay wasn't as convincing, so they did something else. One last little amusing point. That's the stratosphere's temperature. Going up or going down? Going down. Going down 2 degrees in 50 years. So not proof, but consistent with surface temperature going up, stratosphere going down is consistent with greenhouse effect, not solar radiation. One more slide. And this is just a diagram I took out of the IPCC report, which just shows what I mentioned before about how if you add a greenhouse gas and the temperature profile is like this, it'll get distorted. So you get a warming in the lower atmosphere, a cooling in the stratosphere, and somewhere in the radiative temperature of the atmosphere, it's about the same. So that's all I have to say, so I'd be glad to take more questions. Although I've been